So we have a very big event this morning. In my career, in all my career, whether BCI or other schools, I have never had the opportunity to host a Nobel Laureate at the school I was at. So I hope you guys are ready to learn some stuff this morning. We hope you'll have an opportunity to ask some questions at some point as well. But we're going to start off by introducing Dr. Shapiro. Dr. Shapiro is the man who runs the program that brings Nobel laureates to schools across the country. So Dr. Shapiro, if you want to come up and tell us a little about the program.
Good morning, dear students. Nobel laureate, Professor Friedman, the honorable guests, members of the faculty and central administration, and this is I'm supposed to say good morning. This is what we do. We bring Nobel laureates to meet with schools across the country. We've done it over 70 times. But the first, what I'd like to say is to express our deep gratitude to Mr. Hughes, Mr. Hammond, Mr. Barroso, for having all this remarkable assembly arranged for us. Let us give them a thunderous round of applause. We visited California, Massachusetts, Hawaii, Chicago. We met with over 10,000 of your peers. And as a result of all, I created a mission, a vision for all of us, what we are up to. And we would very much like to wish you great success in all what you do, you and your families, that you become successful in life and follow in the footsteps of Nobel laureates as long as you live. At this point, I see you and I cannot keep myself until I say, you all remind me of Nobel laureates, because there is a great resemblance I can see. What are the features which describe you best? What I think is pretty much, number one, curiosity is a main feature for Nobel laureates. It is one of the main features for you. You are curious. Is it right? Yes. Thank you. Number two, what describes a Nobel laureate is diligence. And you are diligent, are you not?
Yes.
What describes a Nobel laureate is they are humble and use sword. Are you humble?
Yes.
And they are exceptionally honest in their work and life. Are you honest?
Yes.
You are all well qualified to become Nobel laureate. Trust me. The whole idea of Nobel Prize came out some 120 years back, after Dr. Alfred Nobel passed away. Before that, he created the prize and for the foundation. Nobel Foundation came to work in 1900, and the first Nobel Prize was given in 1901. Since that time, over 900, close to 1,000 people received the award. However, it did not go smoothly because everything was accelerating, and today we have about 30%, more than 30% of all Nobel laureates over century time, because we live an accelerating era. And you are a main reason why it happens, because you are pushing the whole mankind ahead with your questions, with your curiosity, your resolve and worries. Out of 6 total, and I always in physics, chemistry, physiology and medicine, literature, economics and peace prize. Today we have one of these exceptional people, humans, Dr. Professor Jerome Friedman, who won the prize in 1990 when he and his collaborators discovered what? Who remembers? Right! And it will be discussed in great detail. And we hope you will ask tons of questions about it. Did you read his Nobel lecture? Did you? Anybody?
Yes.
Thank you. Thank you. So Jerry, please be ready. At this point, it is my privilege and honor to introduce a Nobel laureate role model, Professor Jerry Friedman, and let us give them a great hand.
Thank you for your very kind introduction, and thank you for your applause, and good morning to you all. It's a pleasure to be here today to tell you a little story about how humankind has come to understand the structure of what we are all made of, namely atoms. So the question is, are we really made of quarks? And the answer is, of course, yes. If we think about it, we're only made of 3 different types of objects: up quarks, down quarks, and electrons. And everything around us, these are the fundamental building blocks of nature And everything around us is made of the same thing in different combinations. Isn't it remarkable that everything we see around us is made of 3 different objects, only 3? And so I want to tell you how physicists came to this conclusion. First of all, I'd like to talk to you about physicists and how they actually study things. They study things at different levels of magnification. And for example, if I want to study bulk matter, let's say I have a magnification of 1. But bulk matter is made of atoms. If I want to really study the structure of the atom, I have to have a magnification of 100 million. And then, if I see the atom, I see electrons going around a tiny nucleus. And if I want to study the small nucleus, I have to have another magnification of 100,000. And then if I say, oh my goodness, the nucleus is made up of neutrons and protons, and I want to study what's going on inside with some detail, I've got to have another magnification of 10,000. So you see, in order to understand matter, we have to look at the smallest possible sizes. And I'll tell you a little bit about how we reach these sizes and how we can use accelerators to study these things. Now, the story begins in 1911, a very famous physicist, Ernest Rutherford experiment, in which he had radioactive radium shooting alpha particles. Now, alpha particle is just the nucleus of the helium atom, and it's scattered from a gold foil, and the scattered alpha particles hit a zinc sulfide screen and made little bits of light, and people actually with microscopes look for little bits of light coming in the screen. And what they noticed was that the alpha particles scattered at large angles. And this actually brought about the first idea of what the structure of the atom was. And let me tell you how this was interpreted. So there were 2 models at the time. One was called the plum pudding model. It was proposed by J.J. Thomson in 1904. And you see the atom has a positive nucleus surrounded by electrons, negative electrons. And therefore the total charge is 0. And the charge is balanced with it. So the actual atom itself is neutral in charge because the charge is balanced. So J.J. Thomson had the idea that the nucleus was very large and that the electrons were inside like plums in a plum pudding. It was called the plum pudding model. There was a Japanese physicist, Taro Nakaoka, in 1904, who had a different model. He said, well, maybe the positive part is inside and the electrons go around it. He wasn't very specific about what the size of the nucleus was, but the idea was that they were separated and the electrons went around a positive nucleus. Now, imagine the alpha, let's look at Rutherford's experiment. Imagine the alpha particle coming in. When it's outside, it sees no charge. First of all, I have to tell you, it scatters by the electric charge. The electric forces scatter make the alpha particle scatter. So when it's outside the red area, it sees no charge because the positive and negative cancel. When it gets inside, then it starts meeting electrons. And it could scatter from electrons. But the alpha particle is 8,000 times heavier than the electron. So basically it just plows through, the electron can't deviate. It's like a big truck hitting a stone. The truck doesn't scatter. The stone basically is knocked out. So that Rutherford's experiment could not be verified, would not verify this kind of model because there would be no large angle scattering. On the other hand, if the positive nucleus was small, or not necessarily small, but separated, then the alpha particle would go inside and it basically scatter from the positive part. Now it turns out that the positive part was 50 times heavier than the alpha particle. So again, the alpha particles could bounce off at large angles, and therefore, the Rutherford experiment verified this model, where the nucleus was inside and the electrons were outside. Now, it turns out that physicists at that time hated this result. They didn't like it at all. And why? Because if you have an electron going around a positive nucleus, it's going around a circle, and according to the laws of physics, it would radiate. Because when you go around a circle, that is equivalent to a type of acceleration change, the velocity is changing. And therefore, the electron would be continually radiating, and an atom would basically decay away in about 10 to the minus 10 seconds. You know, if I say 10 to the minus, I mean 10 to the minus 10th power. And so therefore, matter could not exist. So the only way out of this problem was to develop a new theory called quantum mechanics, which actually saved that structure of the atom and made it reasonable. Now, here is a picture of Rutherford with the student Hans Geiger in 1912 in Manchester University. Hans Geiger was the inventor of the famous Geiger counter, which you've all heard about. And you see the apparatus on this little table. That's the size of the experiment. So then later, the structure of the nucleus was uncovered. Rutherford realized, so it was realized that the nucleus was made up of other particles, and one of them was the so-called proton, and the proton, Rutherford identified the proton as being the nucleus of the hydrogen atom. And then Chadwick in 1932 discovered the neutrons. And therefore, it became clear that this nucleus was made up of two other particles called neutrons and protons. But the question came up was, are these particles fundamental? What I mean by that, are they made up of any other particles, or are they just made of just one substance? And it took 40 years to answer that question. And this is what I'll be talking about. So great progress occurred after 1946, after the end of World War II. There were new accelerators, new types of detectors, and because of that, a large number of particles were discovered. A tremendous number of particles, different types of particles. They were all called elementary particles. And one of the major things, reasons that one could discover these particles was something called a bubble chamber. It was a detector in which you could actually see particles interact. Now, this is a picture of a bubble chamber in which a gamma ray is coming in and making an electron-positron pair. If you look closely, you can see, now this bubble chamber was placed in a magnetic field, so charged particles would have a curved orbit, because the magnetic field would make a moving charged particle have a curved orbit. And now gamma ray is electromagnetic radiation. Now light is electromagnetic radiation, X-rays are electromagnetic radiation, light is electromagnetic, gamma rays are just, but they have higher energies. So basically, you can think of gamma rays being like light, but much more energetic. And this gamma ray comes in and creates an electron-positron pair. So just by looking at this picture, you can tell two very important things. The gamma ray can make a pair. You can go from basically a energy, something which has no real mass, could make two massive particles, namely electron and positron. And that's the first thing. And the second thing, as you've discovered, antimatter. Because a positron is an anti-electron. So this one picture can show you two things. And therefore, there were many, many different pictures taken and many, many things were analyzed. And as a result of that, and I want to tell you that today, we don't do it visually, we do it electronically. Here's a picture of a very high energy accelerator with electronic readout of of the same thing. You can look at tracks electronically. So we don't do it in the same way, but it's the same basic principle. So basically, by 1960, many particles were discovered. And then the people said, what do you do with all these particles? It's ridiculous. And Fermi, Enrico Fermi, the great physicist, said, if I could remember the names of all these particles, I'd become a botanist. And so it was that kind of situation. And so basically, two physicists, Bellman and Lehmann, in 1961, organized these particles according to a mathematical group called SU3. Don't worry about what that means. It's a mathematical group. It has really nothing to do with physics, just mathematics. And they were organized into families, according to spin. Now, the thing about these particles is that they have the properties of a spinning top. And but we have to define them in terms of what we call quantum numbers. But don't worry about that. I just want you to have the ideas. There'll be many things that you won't totally understand. But what I want you to do is get the picture. So they organized, it was called the Eightfold Way. And it was like the periodic table of the elements. How many of you are familiar with the periodic table of the elements? Ah, good. Because the point there was this table accounted for the existence of elements that he discovered. But it also predicted the existence of elements that he hadn't discovered, and they were ultimately discovered. This is the same thing. It accounted for the existence of particles that had been discovered, but it also predicted the existence of particles that had not yet been discovered. And let me show you the families. Here are the families. Each family has a different spin. That one has a spin 0, spin 1, 1/2, 3/2. Every little black dot is a particle that this scheme proposed. And lo and behold, every particle was found. My goodness, what a surprise. And people are just amazed. And how do you account for that? There was no real physics put into it, it was just a mathematical group. So, this is the origin of the quark model. Because in 1964, independently, Murray Gell-Mann and George Friedman said that if you have three little objects of a certain set of properties, you could make all these families. They would have that structure. And that was all there was to it. And this was the beginning of the quark model. So they are the building blocks of all these other particles. And people thought this was a very strange idea. And so, but let me tell you what it was. For example, at that point, there were three types of quarks proposed: up, down, and strange. And now if you say that the charge of the proton is +1 and the charge of the electron is -1, the up quark had a charge of +2/3, the down quark -1/3, and the strange quark -1/3. And people say, oh, that's really bizarre. Who ever heard of fractal charges in nature? Anyway, the way it worked was the proton was two up quarks and a down quark, and you can see it. If I take 2/3 plus 2/3 is 4/3 minus 1/3, 1, charge of 1. If I take the neutron, which is charge 0, it's 1 up quark and 2 down quarks. And you see, if I do that, it's 2/3 minus 1/3 minus 1/3, 0. And that's how it worked. And that was the quark model. And so, and here you can see right here here's one of the families. There was a family on the right, convergent. And you can see how the quark model actually accounted for the structure of this family. For example, look at the very top, 3 strange quarks. The second row has 2 strange quarks. The third row has 1 strange quark. The fourth row has no strange quarks. If you look at if you look here at this corner here, I'm not in the way of people here. So this here. Therefore, 3 up quarks, 2 up quarks, 1 up quark, etc. That's great. That's great. Thank you. That's better. And then if you look at the other side, 3 down quarks. So you can see how the structure of that family came from the quark model. It's very simple. You don't need fancy mathematics to see how the structure of that family came from these 3 objects. But then the question becomes, well, you proposed a new particle. What do physicists do when a new particle is proposed? They search for it. They looked everywhere. They looked at cosmic rays, they looked at accelerators, they looked at seawater, they looked everywhere. And not a quark is found. Not a quark is found. He goes, of course, it's a crazy idea. First of all, these are point-like particles. They have almost no size, number one. Number two, they have fractional charges. Nobody ever saw a fractional charge in nature. And therefore, this is a bizarre idea. And what are particles? What do these particles? What is their nature? They have, for example, the particles that were discovered have a diffuse nature. They have continuous charge distributions, no little objects making them up. And that was the point of view that maybe the quark model was a good mathematical model to represent the families, but in terms of reality, it had no reality. And here are some of the points of view expressed in little things. Murray Gell-Mann, the father of the quark model, said, "Oh, if hadrons or maybe particles are made of quarks, baryons, for example, these particles, it's hard to believe that the particles we discovered are made of quarks." James Bjorkane, who was working in this area, said we would welcome additional data to destroy the constituent model, namely the quark model. Kurt Godfrey, who was also working in this area, said, "Professor Bjorkane and I devised these some rules, namely some mathematical equality, in the hope of destroying the quark model." And then a fellow who, by the name of J.J. Kokody, a theorist at CERN, wrote a whole monograph on quarks and said, of course, it's an ill-founded idea. So that was the state back in about 1967, 1969. And what was the model of the proton and the neutron? There was even a model which I consider very strange, it's called nuclear democracy. You know, I told you about all these particles that were discovered. They all are equally fundamental in this theory. But the thing which is really remarkable, that every particle is made up of every other particle. So, for example, the proton was a pion plus a neutron plus anything else that you could add with the same so-called quantum number. The neutron was a pi minus plus a proton, and anything other. And this was the model. It's almost as if somebody said, I look out at this audience and everybody here is made up of everybody else. And it's a strange idea, but in quantum mechanics you can make it work. So that was the point of view. Now, the story begins to change in 1966 with a new accelerator being turned on at SLAC called the Stanford Linear Accelerator. And the experiments went on from 1967 to 74 at MIT SLAC. And the idea was that you would shoot very energetic electrons and protons and just look at the scattered electrons, and you don't pay attention to anything else that's happening. And this provided the first direct evidence for quarks. Now, I'll explain why. A little bit of water here. It's over here. Okay. So let me give you a little metaphor to actually show you how you do this kind of thing and how it's really looked at. Imagine I gave you a fishbowl in a dark room, and I said to you, you can't put your hand in the fishbowl, but you tell me how many fish there are in the fishbowl. You say, that's ridiculous, that's impossible. And it isn't possible. So I give you a flashlight. You know what do you do? Of course you turn it on. And you look. You can tell how many fish are in the fishbowl. Well, that's exactly what the experiment's all about. You see, instead of having a light beam, one had an electron beam. Now, I want to tell you something. To see something, you need a wavelength. And you know what a wavelength is? How many people are familiar with the idea of a wavelength? Especially in light? Okay, good. However, because of quantum mechanics, particles have an associated wavelength. So an electron can behave like light. And you see, so the electron, with the flashlight, the light scatters off. You see it with your eye. Your brain reconstructs the image. Ah! You can count the fish. You do the same thing with the accelerator. Use an electron beam. It scatters off whatever is in the object you're looking at. It's detected by electronic detectors. And computers put the numbers together and create images. And that's all there is to it. It's the same concept, except that it's much more complicated. So I want to say one other thing, which is very important, and this has to do with the question of magnification. And this has to do with the thought. You know, if you want to look at something with light, you want to be able to resolve it. The wavelength of the light that you're using must be considerably smaller than the other you're looking at in order to get a good resolution. And so what you need to see very small things is very small wavelengths. However, because of quantum mechanics, an electron or any other particle has a wavelength. And the wavelength is something called Planck's constant divided by its momentum. And it's called the Broglie wavelength. And the point there is, by making the momentum of the particle very, very large, you can make the wavelength very small. And therefore you can use higher and higher energies to look at smaller and smaller objects. Isn't that remarkable? That's why physicists build bigger and bigger accelerators. They don't want bigger toys. They want to look at smaller and smaller things. So actually, when Rutherford looked at the nucleus, he saw this. However, if he had more energy, he would see this, where he starts seeing the structure of the nucleus. So basically, accelerators and the detectors are equivalent to very powerful microscopes. That's the point I want to get there. Equivalent to very, very powerful microscopes. You can look at very, very tiny things. So the experiment used the equivalent of an electron microscope. If the slide accelerator had 20 billion electron volt, the electron is very, very high energy, highest energy at the time in the world. The effect of magnification was 60 billion times greater than you would get with ordinary light. So you can look at very, very tiny things. Here's the Spock accelerator. It was 2 miles long. You can see it. What you see is above ground are the places to produce the energy for the beam. The beam was actually underground, as you've noticed. It goes over a major highway. The experiment was done in this building right here, and so that was the slack linear accelerator of those days. And here are the detectors using the biggest instrument in physics at the time. This was the Apd Spectrometer. Notice that there's somebody standing here. You can see that person gives you a scale. The whole idea is you put your target right there, and the scattered electrons would go into these tubes. So this was the Apd Spectrometer 20 that was 75 feet long. This one was 150 feet long, weighed 2,000 tons. And the scattering electrons, you could change the energy you detected by changing the magnetic fields of the magnets here, and you could change the angle by rotating this on these rails. So you could actually get the energy and the angle of every scattered electron, so you could actually reconstruct the images that I was talking about. And here's the basic idea, the same idea as Rutherford. You know, if you had nuclear democracy, you'd have sort of a continuous charge. An electron going through would not be deviated very much. If you had quarks or constituents in the proton, they're the little objects that the electrons would scatter from. Except in this case, the quarks were roughly 10 times heavier than the electrons. So they could bounce again at big angles, whereas in this case, they would go straight through basically. It was the same thing all over again. And let me show you what the results were. So here are the results. This curve would be the old physics. What do you expect from the old physics? What was the curve or these curves? When the images were reconstructed, it was found that these objects that were scattering the electrons were smaller than could be measured, and all that one could do was put an upper limit to the size, and therefore we call them point-like objects. They're point-like objects. Now, my goodness. So it was discovered that protons and neutrons had point-like objects. Wow. That was quite a shock to the community. And so, but the point is, are they quarks? Now, what does one have to show to prove that they're quarks? Two things. They have to show that they have spin 1/2. That's what quarks were supposed to have. And they have to be shown to have the proper fractional charges. And that was the next challenge. Was the quark model true? So the constituents, or were these constituents quarks? So the spin was found out after a number of measurements, and the idea there was by looking at large angle scattering and small angle scattering, one could actually find out the spin of these objects, because the large angle scattering depended more on the so-called magnetic scattering, which depended on the spin, and the small angle scattering did not. By taking the ratio, you could find the spin, it was found to be 1/2. Oh, great! But then the question is fractional charges. That is the big question. So it turned out that one had to have comparisons between so-called electron scattering and neutrino scattering. Now, neutrinos are particles that come from are almost ghost-like particles. They have no mass, they have very, very small mass. In those days, we thought they had no mass. They have very tiny mass. They have no charge. They barely interact with matter. However, if you compare neutrino scattering with electron scattering, neutrinos do not scatter via the charge of the quarks, but they scatter by something called the weak charge, which is, don't worry about it, but it's a different type of force. So by comparing the electron scattering and neutrino scattering, we find out about the charges of the quarks. So this was done at CERN between 1970, neutrino scattering between 1971 and 1974, and this actually was done with a big bubble chamber, with a heavy liquid bubble chamber. Here's a picture of it. It had it was 5 meters long. It had 12,000 liters of freon, and this was done. They took a lot of experiments, a lot of measurements with it, and by comparing the two, you see the ratio of the neutrino scattering and the electron scattering depends only on the charges of the quarks, QU and QB. And it turned out to be correct within the experimental error. And of course, as time went on, the experimental error got smaller. And lo and behold, quarks were discovered. There's no way of escaping it. People didn't like the result. What are their formulas? Because there were constituents in the proton and neutron, they had spin 1/2, they had the right fractional charges. But it took quite a number of years before the community decided to drop all the old models. Between 1972 and 1980, that's the time it took for the community to actually rise and accept the Quark model totally. You see, novel ideas sometimes have a very hard time being developed in science. you can see that science is very, very difficult in terms of actually verifying new and very unusual ideas. So let me say a few things. So I'm going to say a few things because I think it's getting long. First of all, were any free quarks ever found? No. So why do you believe it? Well, because one again needed a new theory, which is called quantum thermodynamics. And in this theory, you see, there's a difference between this force and the other force. For example, if I take an electron and proton and pull them apart, the force decreases as the square of the distance. Wow. So it makes it very weak. I can finally pull the electron away from the proton. In the quark model, with this new theory, quantum thermodynamics, the force is constant. It's almost, in fact, it increases a little bit as you pull them apart. Oh, wow. So it turns out the force between these two little objects is around 15 tons of weight. Can you imagine these tiny objects with 15 tons of weight? That's so-called strong force. If I try to pull them apart by 1 centimeter, I need 10 to the 12 electron volts. 10 to the 13 GeV, not electron volts, 10 to the 13 GeV. GeV is 1 billion electron volts. It's an enormous energy. And to build an accelerator with current technology, it would be the size, to produce that kind of energy, would be equivalent to an accelerator the size of the solar system. Can't do it. And so what happens is I pull two quarks together, apart, the field gets a certain amount of energy, and then it breaks, producing a quark-anti-quark pair, and this is how I produce particles in this theory. So it's a force, it's an extremely big force, and we cannot find free quarks in nature because of it. But there's some other implications which are, okay, let me just say, but we we've discovered 6 types of quarks in nature: up quarks, down quarks, strange quarks, charged quarks, bottom quarks, top quarks. They have different masses. The top quark is extremely heavy. It's heavier. It's comparable to the gold nucleus in masses. We don't understand. These are very, very tiny particles, and they all have spin 1/2, and they all have the same types of fractional charges: 2/3, minus 2/3, plus 2/3, and minus 1/3. And the upper limit of the size of a quark is 10 to the minus 17 centimeters. And I'll tell you a little bit about that. So let's talk about the implications of that. If I take a carbon nucleus and ask the question, how much volume of the carbon nucleus is taken up by the quarks and the electrons, which are the building blocks of the carbon nucleus? It's about 1 part in 10 to 27. Now that's an incredible number, and let me try to give you a picture of what that number is. If I expand a carbon nucleus to the size of the Earth, now think of that, size of the Earth, the nucleus would be about the size of a football field. And in the nucleus would be 36 quarks, and they'd be smaller than grapes. So in that volume, these quarks are moving around, smaller grapes, and you get that picture. You think of 36 grapes moving in a sphere with the radius of a football field. And then the rest of the atom, which extends to the edge of the Earth, would have 6 electrons, or something, 6 equivalent objects smaller than grapes moving around. Now think of that. So what does that tell you? It tells you that all of you are empty space. I'm sorry to tell you that, but you're empty space. So if you're empty space, and this podium is empty space, why can't I put my hand through this podium? Why? Well, there's one simple reason. Fields. Namely, The electrons in my hand are repelled by the electrons in the podium here, and that's why I can't. So basically, your solidity doesn't come from the nuggets of matter that you are made of, but it comes from the fields. Remember in Star Wars there was the slogan, may the force be with you? Well, you're totally electric force. That's what gives you your solidity. And so that's a new version of what matter really consists of. What about weight? Well, let's say I'm a person who's 150 pounds. I say, oh, well, you're only made of quarks and electrons. And I say, okay, I'll take all these electrons and quarks and put them in a weightless bottle. How much do they weigh? Less than 2 pounds. So your weight also doesn't come from the nuggets of matter. Where does it come from? You step on the scale. Where does that roughly 148 pounds come from? It comes from the most famous equation in physics. Who knows what that is? E equals mc squared. And why is that? Well, the quarks are moving very fast in the neutron and proton. And they have a lot of kinetic energy. And that kinetic energy has weight. They also are bound by force fields. And those force fields have energy density. And that also gives rise to weight. So basically, most of your weight comes from the fields and the effects of the fields. Not from the nuggets of matter. And so we have a new paradigm of what matter consists of, what atomic matter consists of. So, but then I can ask the following question. Well, maybe quarks are made of other particles. Why do you say that quarks are necessarily the most fundamental particles of nature? I don't know if they are. If I had to bet, I would bet they are. And why would I bet they are? I could be wrong, but I would bet they are because of the following. If the quark it has an upper limit of 10 to the minus 17 centimeters, I have to fit something in it, namely an object in it, okay? And remember that object has a wavelength. And that wavelength has to be of the order of 10 to the minus 17 centimeters. And when I calculate the momentum of that particle, because you remember, the smaller the wavelength, the bigger the momentum. It's enormous. And if I ask what force field is required to hold it in, it's enormous. So it turns out that there's 15 tons of force between two quarks would have to be multiplied by 100 million to keep objects inside the quark. It'd be a new force of nature which is just absolutely incredible. And therefore, we have no evidence of such force, but time will tell. This is an experimental question. And it's being studied today at the Large Hadron Collider at CERN, which has a 14 trillion electron volt beam, very high intensity, and that will have to increase the magnification by at least another factor of 10. And therefore, it will give us some information about whether quarks are fundamental or not. But it's a fantastic machine. It's a lecture in itself to talk about it. And maybe some of you ultimately will be working on this machine because it will go on for many, many years if they will upgrade it. But it's a very exciting time to be a part of physics today. Thank you very much.
At this time, we're trying to take a few questions. If you do have a question, you can come up to the microphone here. Just sort of form a line. We'll have time for 5 or 6 questions. And then we may have some time for other guys who want to stay a little longer to stay after that. We'll start with a few questions.
What was your inspiration to study quarks/atoms?
That's a very good question. Actually, first of all, I have to tell you I was part of the group, and I want to make sure that you understand that group. That science is is a cooperative, collective activity. When we started these experiments, we were like the rest of the community. We didn't necessarily believe in quarks. In fact, we thought it was a very strange idea. But we also realized that the photon had never really been studied very, very extensively. And we also had a new energy range, which allowed us to study in a way that hadn't been studied before and look at smaller magnification. And we also chose a method to do it, which was very unusual, and actually most people thought it was a waste of time. In fact, when we first proposed to do these measurements, we were told by the program committee, which allots time for accelerators, that it would be a waste of time to do what we were planning to do. So we said, well, we would measure something else and measure what we were interested in as a background. So we spent a little bit more time on the things that we were interested in. And before we knew it, we were getting results which were so unexpected that after that we got all the accelerator times we wanted, and we were able to continue the experiment for a number of years. The actual experiment started in 1967. The measurements continued to 1974. So that's what inspired it. Just the curiosity of what the proton consisted of, with no pre ideas, which would sort of, in a sort of sense, that we're trying to confirm or discard. So this is an example of that curiosity is one of the most important driving forces of science and developing new knowledge within time.
What did it feel like when you learned you were going to get a Nobel Prize? Or what did it feel like when you stepped up?
Oh, it was incredibly. I was so surprised because this was actually occurred in 1990, which was many years later. Since we started the experiment in 1967 and 1990, we'd never in any way supposed that we'd get a Nobel Prize at that point. And I was just totally flabbergasted, amazed, and of course happy. But it was totally unexpected.
So first of all, thank you for coming. My question for you is, was there any technology that you needed to make or tinker with to enable to make this advancement?
Oh yes, there was a tremendous, actually designing these spectrometers was something absolutely new. Making the so-called photoscopes, the electronic detectors was absolutely new. We had to have other types of detectors made so-called direct electronic detectors. And when you do experiments like this, you keep on developing previous technologies, and you could not exist on the previous technology. You always have to operate it because the requirements were more stringent. I mean, we went to much higher energy. The signals were different. We had to actually develop new things. And of course, in those days, computers were very primitive, and it was an extremely challenging thing to get the online computers working and working appropriately. And the analyses required basically mainframe computers. We basically saturated mainframe computers of those days, trying to do the physics analysis of experiments.
So you do of the Large Hadron Collider at least in Germany? The Large Hadron Collider in Germany?
Yes.
Do you know if you can find anything more using that, or is that collider already being used with its full extent?
Oh no, it's just in a sort of sense. If you consider the development and the history of colliders, it's just started. They just upgraded the energy recently to 13 the capacity of 14. They've been running at 7, and now they've gone to 13. And they're in the process of increasing the luminosity, which is the beam intensity, to look at more and more rare events, types of events.
So about how old
how old was I when I started the experiment? Well, we started working on it and actually in 1963 when we decided to go and work at SLAC. It was quite an interesting thing because there were my colleague Henry Kendall, who unfortunately has passed away, also got a Nobel Prize. Where we were partners, and we decided to work. We heard about this new accelerator being developed at Stanford, and of course we were both teaching at MIT. And how in the world do you do an experiment 3,000 miles away when you teach? So we went to the physics department, made arrangements. I think MIT is one of the most understanding universities in terms of giving professors latitude to do research. They made arrangements that allowed us to go back and forth. And so we started actually designing the spectrometers and the equipment about in 1963. So I was 33 years old.
My question is, how many years did it take you to finally discover quarks existed?
How many years? Well, and actually, if you think about it, to really, let's put it this way. We started the experiment in 1967. When the neutrino results and the electron results showed that the fractional charges were there, that's what I consider the discovery in the sense that there was no way of getting out of the fact that the quark model was valid. There was no way of basically contradicting that. And so that was 5 years. Now, in terms of some people, they still didn't believe the quark model. And further experiments doing other things have to be done to actually, which were consistent with the quark model, to actually convince other people that the quark model existed. But I would say 72 was the time that it was impossible to escape the quark model. And then it took another 5 or 6 years before the whole community was persuaded. They didn't fully understand all the implications of some of these measurements. And there was a lot of controversy as to whether the quark model was valid, etc. And I must tell you that when the quark model was being discovered, there were many other theories to explain these particles. And the theorists spent many hours actually fine-tuning these theories to be consistent with our results. They were only partially successful because in the long run, none of the old theories would account for what we observed in these experiments.
We'll do one more question, guys, and then you still have to have people, guys, if you want to stay longer, we'll be able to stay longer.
Well, I say your questions are wonderful questions. You're very thoughtful students, and these questions are at a very high level. Thank you.
How difficult was it in 1967 when you started your experiment to do all the math without the advanced technology that we have today?
It was difficult. It was very difficult. I mean, everything was a challenge. It was, today we have such technology. The technology today is incredible. If I gave you a lecture about CERN, the Large Hadron Collider, the technology there is just beyond description. It's so advanced and sophisticated. In those days, it was very, compared to today, it was extremely primitive. And everything that you did was a challenge. And so it was, and that was, of course, one of the things that made it so interesting, because if something is easy, it's not so interesting. Both the questions, the scientific questions were extremely interesting. But it was also very interesting to push the technology to a point at which we could use it for these experiments.
Thank you.
On behalf of the students at Boston College High School, we would like to thank you for taking your time to share your life, stories, and achievements. It has been a great honor to have such a renowned physicist here today. At this time, we also present you with these gifts as a token of our appreciation, and we hope you accept these gifts. Again, thank you for speaking here at Boston College High School.
Thank you, Dr. Friedman, and Dr. Shapiro for coming in today.